We are very glad to be here at Black Hat to present Miasm. So I am Fabrice Desclos, and he is Camille Mouget. We work at the CEI. In French, it's Commissariat à l'énergie atomique et aux énergies alternatives. You know, it's nuclear stuff. And we'll present you Miasm, which, as he said, a framework of reverse engineering. The project is born in around 2006 and 2007. And it has been made publicly available in 2011. It's written in Python, and it has the particularity that it has its own intermediate representation. You have some website here in which you can find more information about it. So why are we here? We are here to show you Miasm, a framework that is used daily in malware analysis, unpacking, and static analysis, and so on. We have some rules in order to try to do clean code in Miasm here. If you are a novice in Miasm, you can use, for example, some resources. For example, in the code you have doc strings. There is no real full documentation in the Miasm, sadly, but you have a lot of examples in which you have some illustration of each feature of Miasm, which is very interesting to read, and there is a blog spot as well. We want today show a list of features of Miasm because it's a bit boring, so we will try to enlighten only some very interesting features, and we will illustrate them with real code examples today. So first, the basic stuff. In Miasm, you have Miasm has his own assembler disassembler engine, and he can manipulate x86, ARM, MIPS, etc. architectures. It can support ELF or portable executable or raw native bytecode. We can add some custom architectures. Maybe we have a mad guy here who did that, and he will present it, I think, this afternoon. Okay, so to start with, if you want to, everything starts for the bytes, so we have to disassemble the bytes. To do this, we can do this simple code. So we have a container, we have to instantiate a disassembler engine, and we have to disassemble a function which gives an assembly control flow graph, and we can dump it. If you write this code, you have written, in fact, multi-architectures code which can disassemble a function. So, but the real interesting, you have this code in some resources here. But the real interesting things in Miasm is its internal and intermediate representation and language. This language is can be extracted from a native assembly language. So we have a translator between this language and this intermediate representation here. Once you have this core feature, you can do some manipulation on it. We will see those manipulation in a couple of slides. And after, you can use this intermediate representation in order to do some static analysis and so on, which will be demonstrated in a couple of slides as well. To get this language, you can write these lines, which takes the native language and which will translate it into this intermediate language. Okay. This language is based on an abstract syntactic tree and is defined by about 9 words. And you have simple, very simple words, for example, integers and variables, and more complicated words, for example, operators, bytes manipulation, and so on. You have also an assignment, which is here represented by expression affectation. In French, affectation is AF is for affectation, and it stands for assignment, but in English, AS is a bit weird to use. Okay, so those words, there are some rules about this language. The first rule is that each expression has a fixed size and embeds its size here. And another rule is that you can only have memory deferencement or variable on the as assignment, so as left values. Another interesting thing is that the expression operator can take anything, any name of operation, and Miasm can work with unknown names of operators, and it can handle also it can do some propagation algorithm, etc. on unknown operators. Another trick is that an interesting point is that assignments are done in parallel. I will show this later. So, for example, if you want to translate MOV EAX EVX in x86, you have this kind of stuff. So you have an assignment between the ID EVX and the ID EAX. And you can print a human readable version of it like this. So you have simply EAX equal EVX. If you want to read another example is a push EAX, for example. So you have here two equations that are done in parallel. So the update of the stack pointer here and the storage of the EAX in the top of the stack. And in fact, this ESP here has nothing to do with this ESP here. In fact, this one is the source of the assignment here. And there are very more complicated stuff. For example, the comparison between two registers. In fact, when we translate this, we will give a bunch of flags, for example, the zero flags, the carry flags, and they are assigned from a very complicated expression, which is in fact the real equation of the carry flag or the real equation of the overflow flag. So, to illustrate this, we can start with this native x86 language. So we have a proc function, some comparison between arguments, and a return of a value. When we translate this code in intermediate language, it's a bit more complicated here. You can see that we can recognize here the push EVP here. We have the move ESP in EVP, and we have the bunch of equation of all the E flags, which is here, and which is a bit complicated. So we have the jump comparison with jump less or equal, which has its own equation here. So the expectation of EAX and the result here. So the first thing we can do here is to use, for example, passes on the ER to generate a modified ER with some code simplification. For example, most common one is dead code elimination. If you are on x86, you know that in the IB you don't need the E flags at the end of the function. So the computation of the carry flag here is not used anymore. So in its parents, it's not used anymore here. And so you can see that this computation is not needed here. So we can remove it. So if we pass this simplification here, we will have this code, which is a bit more simple to read. Now, but we can do better. In fact, the new feature in Miasm is to explain and represent all the intermediate flags with high-level flags. For example, instead of having very big equations in the intermediate language, we have only the simple operator, which does the same things, but is very simple here. And as well, the jump less or equal will be represented by a new operator here, and which will take all the only parts of the E flags that are used to compute the conditional jump. So if here is a new intermediate representation using this new intermediate language here, with this new intermediate flags. And the next step will be to, it's again a bit complicated, so we have to do more than this. So we will try to do in Miasm propagation, and to do this we will have to use static single assignment. It's a new feature in Miasm which has been added by a contribution by Tim Blazitko and Nico Schmitz. In fact, it's very common as well in compilation to use this transformation in order to simplify code. So it has a very interesting property here. Each register can be assigned only once, so you have multiple versions of the same register. For example, you have EAX0, EAX1, EAX2, etc. And here is the new code. So you can see that the ESP.0 equal etc. And EAX has a multiple version of it here. So now that we are in SSA version, we can do for example, constant propagation, but we will do more than this. In Miasm, it's called expression propagation because we will try to do more than expression constant propagation. To do this, we have some rules. For example, we cannot propagate call operators because a call represents a subcall function. You cannot mess with read-write memory, for example, memory buried. And but as we are in SSA, we can do, for example, register propagation and so on. So here is the actual code. And when we do this, we will do a first step of propagation, so only a single step, and it gives this code. So here we have as source the EAX.0, and this value comes from here. So here, as we don't have any memory write between this affectation and this read, we can obviously replace this value by its source. So it will give this code. So this is the first step, and the algorithm trying to find a fixed point. So after this, it will try to take those equations and put them here in the ERDST computation. So the operator here will be obviously very, very, very long. And we have some high-level reduction. For example, here we have a reduction that says that this operator with those sub-arguments can reduce as this simple comparison. Okay? So we have the final code, which is given like this. And from the x86, we can recover that we have a simple comparison, which is the first argument, which is signed inferior or equal to the second argument. The last step is to remove here the phi, which has appeared using the SR transformation. So using this, it's embedded in Miasm as well. So here is the final version of the code, and we have the intermediate representation of the initial x86 code. And the very interesting point is now that if you have the same code but in ARM, if you use this algorithm, here is the result for ARM. So you have the same result, so except that the arguments have changed. In ARM, you have arguments that pass through a register. So here you have register 0 and 1, which are compared. And for example, if you are on ARM 64, this is the same result here from the native different code. Okay. So now, if you use it in a real code, if you have this kind of code which is written in ARM-sum, in ARM-sum it's a RISC architecture, so it's very verbose. We can reduce this to this. So now for a reverser, it's a bit more simpler to understand the code now. Another one. For example, if you reverse some ARM-sum and you have this function, we can use the same algorithm here. And if you try first to get the intermediate representation, it gives this very complicated code here. And you can so use those algorithms in order to reduce this, and this gives the final result here. So, and for those who are familiar with reversing low-level ARM, you can see that it's a simple function which will try to change the direction port of the processor of the CPU, and it's a bit more simple to read this than the actual native code, I think. Okay. Note that this code is not decompilation. It's only a modification of the intermediate language, and is only get back intermediate language. But we will see that we have some tricky things to generate back native language. You can use this intermediate language in order to do, for example, type propagation, value analysis, or loop detection, and so on. For example, in the next slide, we will show how we can use this intermediate language in order to do code disobfuscation. So here we will try to analyze the LLVM machine. Before going deeply in the native assembly, we will show you the first feature, which is symbolic execution. We will use in the attack of the LLVM. Symbolic execution is a bit like concrete execution. The difference is when you are doing concrete execution on a CPU, a register can have only integers as value, and memory has only registers, integers. And in symbolic execution, a register can have can be represented a number or another variable. So if you have this native code, if you try to do a symbolic execution, here is the result of the first line. You have ECX, which is the result, it's shown like this. It's ECX plus 4. If you do the second line, you have this, EBX equal EBX plus 1. And if you do the comparison between CL and 1, here is the flag that will that are given by the symbolic execution. And you can see here that the 0 flag depend only on the ECX value and the complicated equation. Now we have a jump if 0, and here we have the special register IR DST, and his value is a new expression which depends only on ECX and some integers. So with symbolic execution, we get the fact that we have this equation and we can deduce dependencies of the next basic block. But we have a problem here. In concrete execution, obviously the 0 flag will be an integer and will be resolved, and here it's not resolved. So we don't know where to go if we will go in B or 10. So here, this is a classic problem in symbolic execution. And there are many solutions known here. And we will only, and it's up to you to choose a good solution for you, for your use case. And for example, you can do a state split. For example, you can run on the left side of the branch and on the right side of the branch, and so on. We will show you this with Camille in the next slides. There is another problem with memory accesses. For example, when you try to affect memory using symbolic pointer, it's a bit weird. So in Miasm, the problem is solved using dictionary with, when you have a symbolic memory base like this, we will split this in the symbolic part and the concrete part. And in Miasm, only memory based on the same symbolic base can interfere together. So this is a bit different from the real world, but it solves some problems. Okay, so back to the SVM. In order to win some time, the author of the SVM used virtual machine protection. In fact, for those who doesn't know this protection, when you are compiling a code in native language, it's easy for a resourcer to analyze this language because the x86 language is a bit like his mother tongue, so it's easy. And here, the goal is here to compile the code to a new CPU completely created for this occasion, and to traduce this. But this bytecode cannot be executed directly on the CPU, so you have to embed an emulator of this new CPU in your binary. And in fact, when you run the malware, it runs an emulator which runs on bytecode which represents the original code. Okay. So how do we attack this protection? The first one is to do manual reversing. So we have to find the fetcher here, and so we have to find the core mnemonic one and to see how the VM its structure and so on. Once you have this, you can use symbolic execution to have the raw expression of the mnemonic. So using the result, you can infer what is the VM structure, where are the register, where's the VM program counter, and so on. And once you have done that, you can use now Miasm to automate the recovery of the rest of mnemonics. So for example, if you have the first emulation of the first mnemonic, we have this, and you have realized that the memory at ECX is a virtual memory program counter, and you have the first result here of the execution of the first mnemonic. You can see that here, when you have this equation, you can reduce this as a program counter, virtual machine program counter. So this one equals to the original virtual machine program counter plus 1. So this can be reduced as this equation. So and the other equation can be reduced as this one is the virtual machine program counter. So you can rewrite it like this. So we will write those reduction rules and in Miasm owns. And after this, we will try to symbolic emulate the rest of the mnemonics, and we will apply this reduction, and Miasm will give automatically this kind of equation. So it will give back you the original code of the mnemonic. For example, if you have such equation here, you have such a tree, and the reduction will do this. Alors, here are the reductions. So this is obviously the reductions that I explained earlier. You have ACX, which is reduced as VM struct. This memory defacement gives VMPC. This one gives a register, and we don't know which register is it. 4 will be reduced, for example, as integer. And the lookup at PC plus an integer will give an integer, because obviously it's the immediate value of an opcode. And if you have an operation between 2 integers, obviously it will give an integer. So to illustrate this, we have first this tree. We will apply the reduction. So the first one is to replace ECX by the VMPC struct here. So we have here all the integers will be reduced to int here. So now we have a new structure which is known, which has a reduction rules, and this one will give back regx. This one will give back VMPC here. And so we have VMPC plus int and development memory, so it's obviously an integer. And here we have integer XOR integer, so it gives integer. And we stop here because we don't have any more any reduction remaining. So at the end of the operation, we know that the mnemonic is only an addition between a register and an integer. And here is the result on some mnemonic of the virtual machine. So here we have the result, which is a XOR between a memory pointed by a register and an integer. And we have the same mnemonic, the very same mnemonic, except the memory size has changed. So here it's obvious to see this. Yeah. And now the interesting thing is that we can disassemble the bytecode and re-inject the generic equation and instantiate them using the native bytecode. So we can get back the intermediate representation of the VM bytecode. So when we disassemble this, we recover, we will do a demo of this. So here we rewrite only the fetcher of the VM. We emulate all the mnemonics and we integrate those mnemonics, reinject it in the memory bytecode, and here is the result. We have the intermediate language of the whole function which was emulated in this VM. And you can see first that it's a bit complicated because, as you can see, for example, we have a register which is a constant here, and we have the constant which is added with another constant, so obviously we can merge them in order to generate the constants. It will mean me something. Here you can see that we can use the previous algorithm with SSR propagation and so on, and if we did this, we obtain the next result. And here we have the original code of the VM without obfuscation. And but it's in intermediate language, so it's a bit weird to understand. But in Miasm, we have a path which can take the intermediate language and translate it into LLVM language. And so we can obtain this. And the best part is that we can use this LLVM language in order to compile it to native x86 language. And so we can obtain this. And we can obtain a binary. We can inject in the original binary of this VM. And when we run it, we recover the original command and control URL. So all this work is correct because the code has been compiled and executed on real code. The interesting thing is that now our JustVM version is very, very, very quicker than the original one because everything on the VM has disappeared and it has been translated into a native language. Okay. Another interesting part in Miasm is to analyze malware. For example, in equation group, you have an interesting stuff. The binary itself is not ciphered, but every string used in the binary is ciphered. And each time the binary wants to use a string, it has to decipher it in memory, use it, and to wipe it after this. So for a reverser, you have, if you want to do a static analysis, in order to recover those strings, you have to manually take the function, take the crossref, and take back the pointer to the cipher string, the length of the cipher string, and to do some stuff afterward. And we will show you how to do this automatically. So we will use an algorithm which is called the dependency graph. I won't explain here because it's a bit long. It's a bit between the useDef chain and the path and CFIT chain, which can explode with big loops. And in this case, our algorithm is okay. If you want some details, you can see the slides here. So the demonstration is we have, imagine we have the equation group binary. We have recovered the deciphering string function. And so we will show you a usage of the function. Alors, NTEVTX 64 and X 61. Okay. So here the register R8 is used to store the length of the ciphered function, the cipher string, and EDX stores the pointer of the cipher function. When you reverse this, it's obviously that RDX the pointer is here. And the length is a bit harder tricky to recover. Here the R8 depends on R12 and 23. And if you click here, you can see that R12 is initialized here with FF. So what we are doing with on IDA, following the yellow stuff and so on, can be done with a dependency graph. So here we run the plugin in IDA. We say on the call, we want to backtrack, for example, R8, and Miasm will give you automatically the lines which contains the instructions that will give the result in R8. So we will do, and we have as well a symbolic execution engine. We can do this on this instruction, and here Miasm says that the value is only, and there is one value and one possibility, which gives R8 equals to 22. And if we are, for example, if then else, it will track in both branches, etc. So now we have that. We can automate to recover for each crossref of the function all the arguments. And after this, we will try to. The result is that we have all the values of those arguments. The interesting things now is that we will use the emulation mode engine of Miasm in order to emulate the deciphering function and to get back the result. So to do this, here is a simple example in order to emulate a function. So we had a memory page here with the bytecode, with the native code, and we initialize the stack, and we run the code. And for a special example here, we will do this, but additionally, we will initialize the register using the recovered argument and the length of the string and the pointer. And when we do this, and after we will get the memory back to Miasm. And when we do this, we have the following result. Here, Camille is running this script on the world base. And here you can see that you have the detection of the arguments, the recovery, and the emulation. And for every string, you have output the deciphered string. And moreover, the script will get back the result to IDA. And if you go back to IDA, if you look at each reference of the decrypt function, you have maybe it's a bit too little, but you have all the results for each call. So here we use this string. That's all for the intermediate language, and here is Camille now on the emulation part.
Okay, so regarding the equation group DLLs, you also have some cryptography inside, and the idea is to reverse the code on just one DLL discover the cryptography, and then try to identify this crypto in all the DLL, including on different architectures. So how do we do that? There are already a state-of-the-art. So for example, there are static approaches like FLIRT in IDA, but we'll use a dynamic one. Why we'll use that? Because, for instance, here is a memcopy, which is a naive implementation. It's quite easy to recognize it, but you can have the same memcopy but obfuscated. For instance, if it has been written by an intern, or you can have a vectorized version with the SSE extra. So what we'll do is actually consider the function as a black box. We'll choose the input, that is to say the arguments and the initial state of the memory, run the function in a minimalist environment, that is to say just the stack, just a stack and the binary mapped, and if it reaches the end, we'll check the output, the output value and the output memory, the final memory. If it's match the expected one, we can say, okay, it's maybe the function that we are considering. So for instance, if I have a black box, I try to use the signature for multiplication with 5 by 10. I run it, it crashes, so obviously it's not a multiplication. Then I try to use strlen with the hello strings as a read-only in memory. It runs to the end, but returns 0, so it's not strlen. And then I try A2L with 1, 2, 3, 4 as a string in input. It runs to the end. It returns 1, 2, 3, 4 as a long. So I can say, okay, this is the expected output for A2L signature. So it's maybe A2L. So regarding the implementation, we have to be resilient to crashes because it can take fault, of course. If the function expects a pointer and you give him 5, it will crash. So as we are using the emulation in Miasm, it's emulated, so there is no real crash. The infinite loop have also to be taken into account. We just use timeout. The idea is to have a test signature description which is as simple as possible and arch agnostic if possible, and calling which doesn't consider the calling convention. There can be several calls to be sure that this is the function, and it is a problem which is obviously embarrassingly parallel, so we will use this. So all of these things has been implemented in a tiny tools which named Symbolic, which based on Miasm, which is also open source. And one thing that I really don't talk about today, but using the symbolic emulation of Miasm, we can also learn automatically new function signatures. But this is for another day. So getting back to our EquationDrug crypto, we'll just consider the big num part. We have reversed it, so we want to discover it. So we just create a simple test case. Then we prepare the test. We prepare the initial memory. So we just allocate to big num. Then we set the arguments. We run the function, and at the end we check the final state. If it's matching what we expect, we can say, okay, it's a big num copy. So it's just one test. So this is the one slide test which is discovering big num copy. So as a demo, I will try to I will run this code on two binaries and two DLL. One in 66 and one in 32, 64 and 32, sorry. So we already implement some of tests for the big num cryptography. And then if I run it, if I run it on the first binary, it runs in parallels, and it will discover some of the signature that we just implement. So the multiplication, the big num to strings, comparison, etc. And I can run the same test on a binary which is in x86 32 bits, and it also found some of the bits. Simulation is not so slow because you are using some just-in-time compilation, but it's just a implementation thing. So we have seen the emulation as a tiny emulation with just the code and the stack, but we can do more. So for instance, if you are analyzing a shellcode, which comes from Angular exploit kit, this is the landing page, you get through the exploit, then you get the shellcode, you want to analyze it, so you disassemble it, you realize it's encoded, and we can say, okay, we just emulate it to let him decode himself and get back the information. So if we just use what we've done so far, that is to say only the code and the stack, we run the shellcode, and Miasm will crash, but it is normal. It's kind of a try and die approach, because because the emulation is minimalist, it will put your finger just on exotic things when the shellcode is trying to do something that is not quite usual. But actually, he has been decoded himself, so we can get back the memory and inspect why is there a problem, why is there a crash, and inspecting it, we'll find this code. So this is this is a common usage of Windows internal structures to obtain imports to resolve imports based on Windows internal structures. Okay. So how we'll do to continue the emulation, we'll use the so-called sandbox in Miasm, which actually add, in addition to the stack and the shellcode, add some DLLs in the memory. We'll load it. Then some information on the loader, on the Windows internal structures, and a TOB, a PEB, etc., and so on. Actually, the memory in Miasm being a byte precise, we can split for instance, the TEB in just 4 bytes that we know, then skip other sparse structures, actually. So this way, if the malware is trying to reach an address that we don't know, because this is an exotic behavior, like getting the number of CPUs, it will crash, but it will put a finger just on the code that is trying to do something nice. So using that, we'll run the code, and actually Miasm, we will, when it will load the DLL and create structures, it will treat fake address for each of the API. And if the code is trying to call one of these API, it will break on it and say, okay, this code is trying to call coinitializex. So what we can do here, we can go back to Python and write function stub. So for instance, if we want to stub strlen, we have a naming convention, then we can get back the arguments from the sandbox, knowing the ABI. We can get back the Python strings, and we can compute the strlen in a full Python, and at the end, set the returns value and let the emulation continue. We can also have some interaction with the VM, like a custom allocator, or we can write minimalist implementation, like for this function, you will download to file cache. You can say, okay, it always works. It does not actually contact internet, but it always works. And the final binary is named Toto. So, as a demo, okay, so now if we run the code, if we run it with just the code and the stack, we have this crash. She's not always doing. Yeah, okay. We have this crash because we are not simulating the segments in Miasm. We are not simulating Windows internal structures and so on. So now we can say is there an option to enable it, and we go further. And this time we will end on the famous okay, it's trying to call coinitializex. So we can add a stub, and if we do this for some of the function, for like 5 function actually, and if we run back the binary, And if you just look at the results, what we can see here is that actually the code has called URL download to file cache. So we got the URL of the CNC. Then we can see that he has downloaded at foo.exe, that is our name. And we can see after he's doing shell execute and kernel create process, etc. What we can also do is reuse this same script to analyze shellcode from the same campaign by just reusing it, and it will work, obviously. So we capitalize a bit our previous analysis, and we get the new URLs. So far, we've seen emulation from very minimalist, only the code and maybe a stack. Then we had segment handling, Windows structures, then Windows API simulation. But we can go further. Very recently, we had the full userland emulation. That is to say, the code, the full userland run, and just the kernel is simulated, only on Linux for now. So, for instance, we create a Linux environment which will simulate the file system, the network, etc. Everything is simulated. So we have to get back the loader inside the sandbox. We have to map it, relocate it, prepare the environment, say what are the arguments, what are the environment, what are the auxiliary vectors, etc. And as we have done for the function stubbing before, we can stub the Syscall. So we can simulate them. So for instance, if I want to write a generic Syscall write, what I can do is to just parse the arguments, knowing the calling convention, get the memory back from the VM, and call it and call write on the fake file descriptors. Then I associate it to the correct Syscall number, and it's done. So as a demo, there is a full run of a file on a LS. So everything is simulated here. You can see that it's trying to get the magic, because this is the binary file. It's trying to get its magic. We refuse some of them. Then you read the file, apply its rules, and it output, okay, I detected that it's a ELF64-bit. To show you that I'm not cheating, I can also run it for instance, LS, not LS, not file, just LS on ARM. So here I can't use my own Syscall. And trainings, we are simulating get dense, etc. And we get the write at the end, which is outputting the output of LS. So now we've seen the IR use. We also have seen some of the emulation part, and we can try to mix them together. How we'll do this? We'll use one of the common techniques, which is called dynamic symbolic execution. It's nothing new, but the principle is very simple. Actually, if you have a symbolic execution alongside a concrete one, and the concrete execution say where we have to go. So for instance, if I have this minimalist code snippet, the concrete execution is entering the if. If I just run, as Fabrice said before, a symbolic execution, it will get stuck on the if statement, not knowing if you have to enter or not this statement. In a dynamic symbolic execution, we will have a look at what the concrete execution is doing, taking the branch. So we also take the branch. But as we are taking the branch, we can add a constraint on the current path, saying that X has to be odd. And we accumulate some of this constraint along the execution. So what are some usage of this method? So for instance, we can say when you take the if, you can say, okay, is it possible to find a solution which does not enter the if statement, but else, for instance? And if so, can you create, using a solver, can you create an input that will reach this statement? So it's used basically to expand coverage, and it's very useful in fuzzing, like it has been used in the vulnerability research and like in the CyberGrunge challenge a few years ago. So using, for instance, what we've done before, we can create 10 bytes file named target, fully run the file binary on it, break on the read Syscall, which is reading target bytes, turn target bytes into symbolic one, and then we will run until the next Syscall. But each time there is a branch which acts on a symbolic bytes, it will try to create a new solution for these bytes. You try to create a new solution which take this new path, and this way you can expand your code, branch, path coverage, etc. So, as a demo, if I run what I just said, so for now this is just the one that we've done before. We get to the Syscall read. Now it go to the symbolic execution and try to maximize the code coverage. So it found an input which out ASCII text, then an output which out data, then an output which out international I don't know what text, Itachi, etc., etc. So it's quite useful for fuzzing. Another usage of the DSE is to restrain the input, based on what you want in the output. So just to be more concrete, I will get back to the shellcode. And we've noticed that it's packed to be alphanumeric. So what we want to do is to have a shellcode which looks like similar to this one, but use our own CNC. So for instance, using a blackhat.com CNC. What we will do is use the DSE attached to the jitter and say that the input shellcode is fully symbolic. So the decoding routines will run on symbolic bytes. And at the end, we'll have the equation of the output, of the memory output, giving the input shellcode. So as an example. So what we will do, actually, we just fixed the final URLs to be ours. Say that we also want that the initial shellcode has to be alphanumeric, and ask a solver giving its constraint to find a new shellcode. So if I run this demo, it takes just a few minutes, but we don't have time. So here is the output. This is the shellcode that it just created. It's alphanumeric. And if we used the previous script that we just used to analyze our Angular campaign, we get back our own URLs, like blackhat.com. So if you are using this shellcode, it will actually try to reach a payload from this URL and look like an Angular coming from the Angular campaign. So to conclude, if you have just some idea to take away from this presentation, is that Miasm has a framework that there is no magic here. It just embeds some of the common parts that we use every day. So, for instance, the emulation capabilities from just a function or just a code snippet to a full binary. We also have the IR use with some weapons like symbolic execution, can be used for the obfuscation for a lot of things, or just analysis. And it's a framework that we daily used on real-world samples and real-world tasks. So it's we continue to improve it, and we continue to add to bug fix and to add features in it. So maybe it's framework you want to add to your toolbox. We are completely open to suggestions, to contributions, to feedbacks, to beers. There are a lot of works to do regarding abstract analysis to enhance what we present today, etc., etc. So thanks for your attention. I hope the French accent doesn't ruin everything. And if you have maybe just one or two questions, I'll take them.
Thank you.
Thank you.